All right, so we finally made it to waves and vibrations. This will be what we finish up on, and this is sort of a hodgepodge of different parts of the textbook we're using at least this semester. So we're going to jump around through the textbook a little bit, and essentially what we're going to do is we're going to talk about the anatomy of a wave. Then we're going to talk about how that relates to sound, and then we're going to talk about how that relates to light. So let's go ahead and move into the first topic here. So a vibration, the easiest way to describe that would be just a periodic wiggle in time. And then if we extend this from a vibration to wanting to define what a wave is, well, then that just becomes a periodic wiggle in both space and time. So it's important to note that we have both of these going on here, the space and the time. That's what a wave is. When we talk about musical instruments, we don't really care about the space that they fill up, just the sound over time. So it'd be more of a vibration if we're talking about musical instruments. So a wave always extends from one place to another, which basically means it propagates. Honestly, I'm not sure if I spelled propagates correctly, so you may want to look that up before you write it in your notes. We have sound, which is a mechanical wave. And any sort of mechanical wave is just the propagation of vibrations through a material medium. So it's got to be some sort of solid, liquid, or gas. You have to have something to transfer the sound. If there's no material to vibrate, then no sound is possible, which means sound cannot travel in a vacuum. That's why if you scream in space, no one can hear you. Now, light, on the other hand, this is a vibration of electric and magnetic fields. So you have to have both of these together, electric and magnetic fields. That makes a light wave. So we have this electromagnetic wave of essentially pure energy. You can think of light as both photon particles and waves. It's weird, but light behaves as both a wave and a particle. And these are pretty much a representation of pure energy. Light does not need a material to propagate. And that's why we actually get energy and sunlight from the sun. It can travel through the vacuum of space between sun and earth. So one of these you can think of as needing a medium, mechanical wave. Then the other one you can think of as sort of its own medium. And it doesn't have to travel through anything. It just travels by itself. And for those of you that have taken pre-calc or higher or math 3, if you did high school in the US, you'll be familiar with a sine wave. Basically, a sine wave is just a picture of, or a sine curve is a picture of a wave produced by simple harmonic motion. So when we talk about vibrations and waves, we're talking about, essentially this is what they would look like, a sine wave. Well, if you want to get really philosophical about it, I guess no one really knows what a wave looks like for real, but when we want to draw one, a sine curve actually fits the same characteristics. So this is our best representation if we want to draw a picture of a wave, but what's actually happening, who knows? That's not necessarily true for sound waves, but for E&M waves, I mean, you have wave particle duality going on. No one knows what that actually looks like, but we can at least draw simplified pictures of it with waves. So Galileo discovered that the time a pendulum takes to swing to and fro through small distances depends only on the length of the pendulum. So now we're actually going to get to experiments and start getting the fundamentals. So right now we have this picture of a wave. We need to start putting some math and some labels on it to understand what's going on here. And Galileo is sort of the first one to do that. Um, and this is a really interesting feature that he found out, that the length of swinging pendulum, actually, it doesn't depend on the mass at the bottom. So if you think about a swinging pendulum, this thing's going back and forth. What's wild is the mass doesn't matter. So this could be heavy or not, doesn't matter. The only thing that does matter is the length. So the time of this to and fro swing, so essentially to go out and then back, is called the period. So just one complete cycle, however long that takes, is the period. So this doesn't depend on mass at all, and it just depends on the length of the pendulum, and it doesn't even depend on the size of the arc. So really, if you start it higher, if you start it lower, it's always the same time. So you could barely move something off of its center line, and however long it takes to make one period would be the same if you let it go from up pretty high, like 10 degrees. So as you might expect, a long pendulum has a longer period than a short pendulum. So basically, it swings to and fro less frequently than a short one. You can see that here in this GIF that's hopefully playing. We said on the previous slide that, there we go. We said that a pendulum only depends on length, but there is one more piece to that. On Earth, it only depends on length, but if you start taking your setup and going to other planets or to the moon, well, it turns out that the period also depends on gravity, but generally that's the same everywhere on Earth. So as long as you're on Earth, you can say that the pendulum pretty much depends on, or the period of a pendulum depends on the length. But keep in mind, if you change the gravity of the situation, you would have the length and gravity to deal with. Now, the reason we say that, at least for a sound wave or a mechanical wave, a sine wave works, what's actually going on with the mystery of the photon, it's hard to describe, but we can actually demonstrate with mechanical wave exactly how the sine wave here is generated. So if we were to attach a bob to a spring and then we pull it down and let it go, this is essentially what we would see. Now, let's take a look at the setup here. So here is originally where the bob would set. Okay, so this line here, that is its essentially its equilibrium position. This line here. So that's where it wants to be. If we just put the mass on there and let it stop moving, it would just dangle right there where the green line is. But clearly what's happened is we've either pulled it and let it go or pushed it up and let it go. Now you'll notice in our setup, we have a piece of chalk here or a pen or something. Okay, now that's actually going to draw on this piece of paper. You can see from these blue arrows, this piece of paper is moving, right? And while this thing's bouncing up and down, it's drawing on this piece of paper that's moving to the right. So what's happened is this bob is horizontally stationary, it's just moving up and down. As it does that over time, because this is our time as the paper moves by, over time it's going to trace out this sine wave. There's a lot of components here to a sine wave that we need to talk about. So the high and the low points of a sine wave, the high points are called crests. So this is a crest. The low points of the wave, these are called troughs. And then the amplitude just refers to the distance from the midpoint to the crest or trough of the wave. And this says the midpoint, but another word we could use for this is the equilibrium position. So here our amplitude's already labeled, but we can label it here, here, and that is our amplitude. And then of course the wavelength of a wave is just the distance from the top of a crest to the top of the next crest. You can see we have that labeled here. So here's our wavelength. You can say it's from crest to crest. You can also say it's from trough to trough, or really just any two successive identical parts of the wave. So you can see here, you've got this area of the wave where we start down and go up, and it's below the equilibrium. If you can find that very next one where you start down, go up, that would also be the wavelength. Notice I'll do this in black. It would not be here, right? Even though this is the same position, you have to make sure you're going in the same direction. You got to have the not just the same distance from the equilibrium. You also have to, if you think about riding along this wave, you got to make sure you're going in the correct direction as well. So that's why it would be from this upward piece to this next upward piece. And of course, here's just a quick GIF showing exactly how this would be traced out. Now, how frequently a vibration occurs is determined by the frequency of the wave, or the frequency of the vibration. The frequency of a vibrating pendulum or a spring is basically just the number of to and fro vibrations it makes in some given amount of time. So we have a definition of frequency down here at the bottom of the slide, but we can write it out this way. So the frequency, which we represent by F, is just the number of oscillations. And a full oscillation is when you go out and back again. So peak to peak, trough to trough, that kind of thing. So number of oscillations, I'm going to abbreviate it OSC, over some time interval. How long did it take to actually do these oscillations? So time interval. So one complete oscillation is one vibration. The unit of frequency is called the hertz. So if you have one vibration per second, or one oscillation per 1 second, notice the upstairs numerator doesn't have a unit, but then the bottom does have a unit. The bottom is in seconds. So really this is called inverse seconds. So 1/1 is 1, inverse seconds, seconds to the -1, which that's just 1 hertz. Okay, so the unit of hertz is the same thing as an inverse second. Now we know what the period is, and we know it's the number of oscillations over a time. Nope, sorry, the frequency is the number of oscillations over time. The period of a vibration is the inverse of that. It's how long it takes for one complete vibration. So if the object's frequency is known, then we can simply calculate its period. Because there is a relationship, these two things are reciprocal of each other. So it turns out frequency equals 1/period. So we can calculate the frequency this way. And then whatever number we get out of that, we can just do 1 over that, and we can get the period. Now, if we simplify these equations and use less words and more symbols, this is what it's going to look like, because period is represented by capital T. I don't know why, it's just always been like that in like every physics textbook. I guess the capital T means the total time. So instead of just using a little t, we're going to use a capital T to signify that it's the time of one oscillation. I don't know. So let's look at this example. We have a gust of wind. Oops, this should say makes, as there, a gust of wind makes the Willis Tower in Chicago sway back and forth, completing a cycle in 10 seconds. What are its frequency and its period? Well, let's take a look. We know that one cycle occurs in 10 seconds. Okay. So that gives us some information about its frequency. So we have the number of cycles divided by the time interval. So we have one cycle in 10 seconds. Okay, well, that's just 1 over 10. It's in hertz because it's a frequency. So it turns out that its frequency is 0.1 hertz. Okay, and this is really slow because it takes 10 whole seconds to go out and back again. So just to give you some intuition, a fractional frequency like 0.1 hertz is really slow, generally when compared to all vibrations. Now the period, remember, we can just do a 1 over reciprocal to find the period. So period is 1 over frequency. We can plug in our frequency of 0.1 hertz. And it turns out we get 10 seconds as our period. So it takes 10 seconds, as said in the problem, for this whole thing to happen. Okay, we have a wave frequency, we have a wave period. We can actually smash these two things together and talk about a wave speed now. So wave motion depends on the medium through which it travels. Okay, so it is medium specific. Sound actually travels through solids better than liquids, and it travels through liquids better than gases. We'll talk about sound waves next time. But for now, just know that whatever sound's traveling through is going to affect its speed. So this, the speed of periodic wave motion is related to the frequency and the wavelength of the waves. So if we want to talk about speed, we got to talk about frequency, and we also have to talk about the wavelength, which we represent as lambda. It's a Greek letter. There we go, Greek letter lambda. Now, did we have this already? Hold on one moment. Yes, okay. So we did introduce lambda earlier. That's how we talk about the wavelength. There's lambda. I knew it was on there somewhere. So we know that the speed is defined as distance divided by time. We talked about that way back. That was one of the first things we talked about, actually. Now, in this case, the distance is 1 wavelength and the time is 1 period, okay? So we're going distance, how long it takes to do 1 cycle of the wave, the time, how long it takes to do 1 cycle of the wave. We know these definitions now to be wavelength and period, distance over time. So the speed of our wave looks like this, lambda over t. Now, we can do something cool here, and we can make a mathematical substitution. We know that the frequency from the previous slide is 1 over t. So we can break this up. We have our distance over time, lambda over t period, distance over time. Now watch this. We can actually pull lambda out front and then just say it's lambda times 1 over t. That gives us the same thing, right? We're just removing the lambda from the numerator. But now we have this 1 over t, which we can just make the substitution. 1 over t is just f. So it turns out the speed of the wave is lambda times frequency. Speed equals lambda times frequency. Now we can look at a quick example of this. If a water wave oscillates up and down 3 times each second, and the distance between the wave crests is 2 meters, what is its frequency? So we can actually, what's its wavelength and what is its wave speed? So we'll actually look at all three here, okay? So the first one is going to be the frequency. That's the number of oscillations over some time period. We want to know what's its wavelength, so the distance between wave crests. And then we want to smash this information together to actually talk about its wave speed. Now we can look at these three really quick. We have the number of cycles divided by the time interval. So it said 3 times each second. It could say 3 times every 2 seconds. It could say 100 times every 9 seconds. You just put in the number of oscillations divided by that time interval. Okay, so we have 3 oscillations divided by 1 second, and that's going to be 3 hertz. We need to know the distance between the crests. Fortunately for us, that's given to us in the problem. We know it's 2 meters. That's our wavelength lambda. And then to calculate the wave speed, we just multiply these two things together. So we have the 2 meters times 3 hertz, and that's going to give us 6 meters per second. Notice that the units are correct. Remember that the hertz is really just inverse seconds, or 1 over seconds. So that's where the meters per second comes from. We get our meters from the wavelength, and then our per second from the frequency, or the hertz. Something else to note, sometimes you might see a wave speed that looks like a V. But this right here is actually, it could be in some textbooks or some websites, this could be the Greek letter nu, which actually looks just like a V. So my nu looks like that. So sometimes you'll see the Greek letter nu being used for a wave speed. You can also just write V. It's fine. Just if you were doing some extra Googling or something, or watching a YouTube video, they might actually use the Greek letter. So if you're wondering why the V looks weird, it's because it's the Greek letter nu. Okay, last thing we want to talk about. What happens if you have more than one wave and it's occupying the same space, same time as another wave? When this happens, the displacements add up at every point. Okay, and this is actually called the superposition principle. You can think about this in terms of crests and troughs. So over here on the right, if we have when the crest of one wave overlaps the crest of another, their individual effects add together to produce a wave of increased amplitude. So what's happening is we're going to have 2 maybe sound waves or 2 light waves coming together, and they're going to occupy the same space at the same time. You'll notice that we have here at this particular time and this particular position, so it'd be some position X, some position time, we have a crest. And notice on the other wave, so we have wave 1, then we have wave 2. Notice it's the same thing. We also have this same crest. So a crest plus a crest is actually going to give us increased amplitude. So if the waves have the same amplitude, the reinforced wave, the output here, the constructive interference, is actually just twice the original amplitude. Okay, so if this has an amplitude of A, this has the same amplitude, we get 2A out of that. Same thing with the troughs. we would get double the amplitude, but it'd be in the negative direction for the troughs. Now, when the crest of one wave overlaps the trough of another, then the outcome actually, they sort of cancel each other out. And this is called destructive interference. So here we have a crest, but then it interacts with a trough. So a crest plus a trough, when you add those together, you get nothing. Same thing over here, we have a trough plus a crest. When you add those together, you get nothing. And this is actually how noise canceling headphones work. There's little microphones that's recording what's going on, and then you have processors inside your noise canceling headphones that actually actively reverse the wave. They flip the wave to make it cancel out. So if this first wave is what's going on around you, your noise canceling headphones are working really hard to produce this bottom wave to cancel it out. And I think that's a very interesting application, and it just shows just how fast some of these processors are, because when you think about all the different sounds going on, how they're all superimposed, so instead of just adding two waves together, you have who knows how many waves coming in all at once. And then you have this processor that can detect that, reverse it, and then play the reverse sound in your ear on top of what's already coming in to cancel it out. Let's see. So the next topic will be sound. I'll stop here. We'll end on superposition. This first part of this module is essentially just to talk about the anatomy of a wave and all the different pieces it has, like amplitude, wavelength, frequency, cross, crest, all of that. Wait, troughs, crest, yes. Okay, and the next time we'll talk about sound and how we can relate what we just talked about here to what we hear.